Okay, so let's continue from last time. So if you remember last time, what I did. So last time, okay, so whoa, what happened just there? What is going on? Okay, sorry. Okay, so last time. So remember we looked at the Laplacian on Rn, and we saw the Fourier transform as a functional calculus for the Laplacian, i.e. given the right class of functions, oops, sorry, I have to cut that out of the recording. So last time we looked at the Laplacian, and then we talked about how we can form functions of the Laplacian by simply taking the psi mapping to f of psi squared. Fourier transform. So this is for a u Fourier transform of u at psi, and then taking the inverse Fourier transform of this whole thing. Okay. And of course, this. So when we talk about the Fourier transform, seeing it as a functional calculus for the Laplacian, we really mean that if you look at how the Fourier transform acts, so if we take the Fourier transform acting on the Laplacian at some value psi, this is exactly psi squared, well, up to some constant, say. So there's maybe the constant popping up here too, of the Fourier transform of u. Okay, so this is what we did. But of course now we want to move away from, so what we've done is we've extracted out the salient feature of the problem, right? So now we want to move to seeing this from an operator theoretic point of view, because that's the thing that will help us build the kinds of things that we want on manifolds. So let's just have a look at so an operator theoretic characterization. So let's take an operator in a Hilbert space which is self-adjoint. So what does this mean? So it's densely defined. And the adjoint of T is equal to itself. Okay, so that is T is symmetric. So symmetric means that TUV is equal to UTV for UV in the domain of T. And the domain of the adjoint now. So the adjoint can be now if you take the L2 adjoint of this operator, it might be a strictly larger operator than T, but it's not. And T of U is equal to T star of U. Okay. So I'm sure you've seen self-adjoint operators before. And I hope that you've also come across the spectral theorem. So for such an operator, there is a measure, and I'm putting this in quotation marks because it's not real valued. So it's a measure valued in the Hilbert space. In fact, it's projection valued such that T of u is equal to the integral of r lambda d e t lambda. Now, so the measure is this object here, right? So and it's evaluating some so this is u in the domain of t, and what we get out is when we feed in some lambda, what we get out is another element in h here, right? So this is what it means to be projection valued, and so this is typically built using the Rees representation theorem. We will consider a more general setup later on, but I just want to just rehash this and just mention it. Okay, so for the moment, let's not get stuck into the details of it. So explicit construction later. Okay, so let's not worry about it for the moment. But what is important is that for a continuous, or more generally, we can also do this for a Borel, but let's not worry about that. Function that's real valued, we just use the expression as before. I mean, here in the Fourier theory, we saw we could just take f of this frequency variable psi, and here we're going to replicate a similar thing. I'm going to write f of t of u as just the integral over r of f of this lambda d e t lambda of at u. Okay, so what's the domain of this operator? So domain of f of t now is going to be equal to the u in h such that, well, we can make this a principal value argument. So let's, because we're dealing with continuous things, we can just truncate t lambda u squared is bounded by t for all r. Okay, so this is, so it's absolutely, so it's just the u for which this is absolutely convergent. Okay, this integral is absolutely convergent. Well, I don't want to get into that. So the question is, what is a Borel function? I don't want to get into that because that's not going to be of consequence to us. Right now, we're not interested in it, but a Borel function is a function for which the inverse image of a Borel set is, again, Borel. It's like a measurable function, but a Borel function, right? But that's not important for us. So we can just forget about it. We just need to really deal with continuous functions here. Or maybe piecewise continuous, okay, at worst case. So the point is that if we now have this function being bounded, so suppose our function f of t is bounded for all t, then what we obtain is f of t, which is a bounded operator that is self-adjoint, okay? So that's an important consequence of this. So, so how does this connect with what we've talked about before? Well, the example is, so let's consider the Laplacian on Rn again. So we had a method of, say, taking functions of the Laplacian. So maybe write, well, okay, so I can say f inverse of psi mapping to, say, f of modulus psi f of u up to some constant is basically the f of, well, I'll write it out in integral form here. So this is basically taking f of, say, lambda squared d e t lambda squared of u. Okay, so I mean lambda. So I don't want to get into too much of it, but I just want to say that it's consistent, i.e., this is consistent with our previous construction. Okay, so I don't want to say more than that. So in particular what we have is that before we had k on 2 power of u, so this is exactly equal to lambda k on 2 d e Laplace lambda of u. Okay, so now I want to talk about a very important theorem. So a very important theorem for us is the following. It's elliptic regularity. So it's regularity for elliptic operators. So let M prime be a compact manifold without boundary, and D is an order M differential operator from E to F that's elliptic. So where EF bundles over M with metrics HE and HF respectively. Then, okay, so maybe I'll get rid of elliptic here, sorry. Let me just say this. So the theorem is that if D is elliptic, then dom D max equals dom D min, and this is equal to the sublet space HM M prime over E. Okay, so this is elliptic regularity. All right. So now what do we do? So let's fix a connection. Fix a connection nabla on E. And say on M prime, right? So let's just denote both connections by the same symbol. And then let lambda naught equal the formal adjoint composed with the connection itself. Okay, so no, this is not a proof. This is the end of the statement of the theorem. Okay, so this is not a proof, this is a construction. Okay, so now we fix a connection. We're not going to prove elliptic regularity. That's beyond the scope of this course. I mean, we'll never get anywhere if we have to try and prove all of these things. I just want to mention it because this is going to be the key to what we're going to be doing. So, you know, if you have further interest in the elliptic regularity theorem, I urge you to look it up. Okay. So now we fix a connection. And let's call this operator delta C. So this is the formal adjoint composed with itself. Let's now take its closure. So we get lambda we define to be, delta we define to be equal to delta max. So this is the adjoint of this connection acting on the closure, right? It's easy to verify that. And this is I should say here that this operator is elliptic. Order 2, right? So this is a second order elliptic differential operator. So from this elliptic regularity theorem gives us that the domain of this Laplacian is equal to H2 m over E. M prime over E, sorry. Okay. So now we can start thinking about powers of this, right? We can look at powers of this operator. And this is, so these operators are going to be order 2k from E back into itself. And these are again elliptic, right? Because the symbols compose. The symbols compose, and it's not hard to verify that if I take the kth power of the operator, this is the same thing as taking the kth operator and taking its maximal extension. Okay, so this is the kth power of the maximal operator. So I should maybe write that here. This is easy to verify. So we take first the maximal operator, and then we take the kth power. That's the same thing as taking the kth power of the operator and then taking its maximal extension. So, okay. And so from this, we again, from elliptic regularity, gives us that the domain of the kth power of these operators is H2k of m prime E. So now we start to see a bit of a picture. Okay, so before we've dealt with fractional powers of operators. Now we have operators where we know we can identify what happens at each even power. So let's make a definition now. So we make a definition that for alpha, which is a positive real number, strictly positive say, we define H alpha, and I'm going to put a subscript here because at this point it's not clear that this definition is independent of the Laplacian, right? So given this Laplacian, I'm going to define this to be dom the Laplacian to the power alpha on 2. Okay? And then the norm is just the induced norm. Is precisely going to be U. It's just the graph norm of L2 over M prime E plus the Laplacian alpha on 2U. L2 over M prime E. Okay. So again, I just want to really drive this home. So by elliptic regularity, we know that the H2M of Laplace M prime E is equal to H2M M prime E. Okay, so we at least know that the spaces are independent of this Laplacian at these integer powers. Or these even powers, I should say, sorry. Yes? So the question was, I only have the top order terms and the intermediate terms don't appear. So you're asking me what happens to the lower order terms in these norms? Is that what you mean? Right, but however, okay, so that's a good question. So what happens to the intermediate? What happens to the intermediate terms? Well, you see, when I take the kth power here, so I already have this, right? So this elliptic regularity estimate is already telling me that nabla to the power of k is comparable to the norm of all of these sums that we had in the H2k norm. Right, so already here we have that the graph norm of this is equal to UH2K. Right? So whenever we write these Banach spaces as being equal, I mean, maybe I should really emphasize that this is also a norm equality, right? This is not just saying, so elliptic regularity isn't just saying that these are equal as sets, but it's saying that the norms are equivalent. So because the norms are equivalent, so I mean, at least at the integer scales here, so the even order scales here, we have an equivalence of norms. So the question really is, what happens in the middle? You know, is this sensible in the middle, because it looks like it depends on the operator. We at least know that at integer intervals it's independent of the operator, the Laplacian that we've picked. Does that clarify things? No, absolutely not. So the question is, do we need something like a Poincare inequality? No, we don't need anything like that, because actually the lower order term here, I mean, we're always working with the inhomogeneous norm. So this is really taking care of anything lower order. So the elliptic regularity theorem really tells us that the norm, so the H2M norm is equivalent to the H2M norm is really equivalent to the norm with respect to the Laplacian. Right? So, in fact, what we will see is that these spaces here, so if you have a higher alpha, the domain is contained in a space with a lower alpha, right? For that, we need something extra. And that includes the norms. So we don't need any Poincare inequality or anything here. In fact, this is a vector bundle. So you have to make sense of what a Poincare inequality is. None of this is scalar valued, right? That's why we have to go through the elliptic regularity. Know that the Sobolev norm that includes all of these lower order derivatives in its definition on the right hand side here can be written in an equivalent form with just the H2M Laplace norm here is the Laplacian to the power of m. So the graph norm of this is equivalent to the graph norm of this. Yeah. Okay, so thank you for that. That was a very good question. Yes? Hey, H alpha. Yes. Yes, please. For the moment, write the H alpha delta in the norm. We will see soon that we can get rid of this, but for the moment, yes, it's important. Okay, so I want to make another parenthetical remark before we move on. So recall that T is a local operator on a function space, say L2 M prime E, if the support of T of U is a subset of the support of U. Okay? Say for U in DOM T. So differential operators are local, i.e. differential operators are local. And so that in particular means that lambda k, delta to the power of k, I don't know why I keep calling it lambda, is local. However, if we look at Laplace alpha, this is not local for alpha in n. Because you could have asked me why. I mean, we have a notion of fractional spaces using the Fourier transform in Euclidean space. Now we're on a compact manifold, so we can cover everything by a finite number of patches and then consider the problem locally. So the reason I cannot and I do not take this approach is because a priori we don't know how to localize. If we look just in Rn and we look at the fractional power of the Laplacian in Rn, this is not going to be a local operator. So that's alpha not in the natural numbers, sorry, yes. So it's not obvious that we can just localize things, right? Because remember, the Fourier transform can spread things out to infinity. So when we're working in Rn, if we have a compactly supported, even if we have a compactly supported function, the support, when we take some Fourier transform of something, can be pushed out to infinity. So it's the reason that we need to really consider this from a more global point of view, at least a priori, is because we don't know that we can localize things. Okay, so we'll build up to that. Yeah, we'll build up to that. So far we have some fractional spaces that, for which it looks like it depends on the operator itself. So now let's try and divorce all of that. Okay, so I cannot tell you all of these things in excruciating detail, but I think it's, my responsibility to at least show you that these concepts exist, so that if you're interested, you can go look it up. So how do we justify the independence of the operator? For that, we really need to bring about something called interpolation theory. Okay, so let's move back into the abstract setting for the moment. So interpolation theory. For Banach spaces. Okay, so again, I just really want to keep everything, my field is always fixed to the complex numbers, right? So let's recall a definition, or you can see a definition if you haven't seen it. So a function f that takes me from some subset of the complex plane to an open subset, right? Open subset of a complex plane into a Banach space B, is holomorphic if the derivative at some point z is equal to the limit as h tends to 0. H is a complex number outside of 0, such that, it's just what you expect, right? So here, of course, we need to take the norm with respect to the limit with respect to the Banach space norm. So it's exactly what you have in the complex world, except now this limit is with respect to the Banach space object. Okay? So this exists for all z in omega. So similarly, we have a notion of weak holomorphic, right? So it's weakly holomorphic. So if for all zeta in the adjoint space, we have zeta composed with f. So now this is again a function from omega back into C is holomorphic. So a very important theorem that is in the very classic literature is that, so it's clear that holomorphic implies weak holomorphic, but the other direction is also true. So this really allows one to lift a lot of the results from complex analysis to holomorphic functions which are valued in the Banach space setting. Okay. So a pair of Banach spaces, B1, B2, is called an interpolation couple if there exists a second Banach space B3, so third Banach space, sorry, B3, with the BI contained in B3 for I equals 1, 2, and the embedding of BI into B3 is continuous for I equals 1, 2. This is not the most general definition of an interpolation couple if you look in the literature. But so in particular, this condition that BI is a subspace of B3 is not usually assumed, but just for keeping things, you know, accessible and tangible, we'll assume that because in all of our examples, this will be satisfied. So what's the quintessential example for us? So let's take B1 equal to, say, H2J, ME, and B2 equal to H2J plus 1. Well, M prime I put before, M prime. So my compact manifolds have a prime. And then let me take B3 equal to L2 of M prime E. Okay? So clearly we have that H, in fact all of HK M prime E by construction is a subspace of L2. But so the reason I always separate out the zero order part of the operator from the operator, yes? Of course. Yes, so that direction is so the question is, does holomorphic imply weakly holomorphic? I mean, that's the easy direction, right? If this limit exists in the norm of the Banach space, then composing it with an element from the dual space, because that's a dual pairing, precisely means that that limit also has to exist, and therefore it's holomorphic in the usual complex sense. But the interesting direction is weak holomorphic implies holomorphic, right? I mean, that's the harder direction. Okay, so back to this example. So it's clear that the HK spaces are contained in L2. So now what do we have? So now we have U in L2M of E. And this is going to be, well, this constant is basically 1, right? So, well, actually there is a constant, sorry. Because I'm not taking squares. So now, you know, I can look at this operator and okay, so this is J minus M plus 1, say, is my operator. Norm, as I wrote before, so here I'm again using elliptic regularity, and this is going to be equivalent to the H to J minus M plus 1 M prime E norm. Okay, so this is, again, this is elliptic regularity, right? So we can see that this is a continuous embedding. Okay. All right. So now, because we have these spaces contained in a larger space, so we can construct, so we have the space B1 plus B2, which is just as we understand it, B1 plus B2 in the space B3 such that BI is in big BI. And we give it a new norm to make it into a Banach space. So the Banach space norm, so the norm that we give it is precisely taking the infimum overall infimum overall A B, okay, maybe I'll call it B1 plus B2 such that X is equal to B1 plus B2. So this is a Banach space now. So B1 plus B2 with respect to this new norm, B1 plus B2 is a Banach space. And it's continuously embedded in B3, right? Because what we started off with was a continuous embedding. The second thing we want to look at is the intersection of these spaces. B1 intersect B2. So the norm for this, we can just simply write as, say, X B1 plus X B2. So this is also a Banach space. And it's continuously embedded in B3. In fact, now we have a series of embeddings, right? We have that B1 intersect B2 is continuously embedded in B1 plus B2, which is sitting in B3. And what we really want to do is to somehow consider intermediate spaces, right? So what we want, intermediate spaces between B1 intersect B2 and B1 plus B2. Okay, so that's really the heart of interpolation theory. So for that, I need to make another definition. I need to look at the strip. So I want to look at the strip x plus iy in the complex plane, such that x is just a number between 0 and 1, and y is free to be whatever it wants to be. So this is just the strip, right? This is the closed strip. So this is 0, 1, this is C, and I'm looking at the strip here. And now I'm going to make an important definition. So I want to define the space calligraphy F B1 B2. So this is the space of functions F mapping from S into B1 plus B2, satisfying the following. So F on all of S into B1 plus B2 is continuous and bounded. Okay? In the norm, B1 plus B2, right? So whenever I'm writing the space here, I mean with respect to the norm that I've written on the space. If I restrict this to the interior, so this is a map from the interior now into B1 plus B2, I want this to be holomorphic. So the third condition is that T mapping to F of IT, I want this to be continuous and bounded from the real numbers to B1 and t mapping to f of 1 plus it is continuous and bounded from the reals into B2. Okay? And now I give this space a norm. So f in this f B1, B2 is equal to the max now of the supremum of t in R of f of it and the supremum t in R of f of 1 plus it B2. Okay, so now we finally have arrived at what we want. So definition, so fix some theta, let theta be a number between 0 and 1. And define B1, B2, theta to be equal to f of theta, such that f is in this space B1, B2. And so what's the norm? So I want to give this a norm, so I want to call this, I don't know, maybe I'll call it B, so of B1, B2 theta is the infimum over all f in this function space B1, B2, such that f of theta is equal to B. And this is a Banach space. Okay, so that's what we're going to find. Yes, so landing in B1 and B2 is fine, right? But I just really want to emphasize that these are now bounded functions. I mean, of course, I'm saying, yeah. Yes, so if I right, so the point is that I want to look at functions. I mean, it could be so how do you know, for instance, that if you take t, so intuitively what this is saying is that all of 0 should map to B1, all of 1 should map to B2. So a priori, you just know that it's a function that lands us in B1 plus B2. So without this condition, so the important part of this condition is really that t maps to f of it is in B1, and t mapping to f of 1 plus it is in B2. That's all that this is saying. The continuous bounded, I mean, you get this from 1 anyway, but I just put it in there because I can, and it just makes things clear. Yeah, okay. All right, so now what is the theorem? So the theorem. So suppose we have two interpolation couples, and B1, B2 tilde are interpolation couples. Okay, so 1. This B1, B2, theta with the norm that I wrote down, B1, B2, theta, is a Banach space satisfying continuous embeddings B1 intersect B2 is contained in B1, B2 theta is contained in B1 plus B2. Okay, so we have some intermediate spaces, right? So the inclusions are all continuous. Maybe I should say satisfying continuous inclusions, right? Okay. B1 intersect B2 is dense in B1, B2 theta for theta in 0, 1. Okay. 3. So T from B1, if we have a map from B1 to B1 tilde that's bounded, and we have T from B2 to B2 tilde bounded, then we have that it's bounded on the interpolation scale. Okay, so I would love to spend lots of time going through interpolation theory, but of course we're limited in time. So the reason I wanted to tell you about this is just so you at least have an idea of the underlying machinery that's required for this sort of thing. So I really urge you at some point in your careers, or to, if you already haven't seen this stuff, to look it up, because interpolation theory is extremely powerful. So now let me give you a proposition, right? So if we have two Hilbert spaces, H1, H2, and these are Hilbert interpolation couples. Yes? Question? It's the same operator. So think about an operator that might be bounded on two endpoints, right? You can have, say, B1 intersect B2 is dense in these spaces. So you can certainly think about operators which are bounded on a dense subset. Say, when you're doing analysis, typically you might have an operator on compactly supported smooth functions, and it extends to an operator that's bounded on all of LP, for instance. So that would be a model of such an operator. So it's the same operator that's defined on both B1 and B2, but it maps. So this is just saying that it's bounded with respect to these induced norms. Okay, so it's the same operator, of course. So it could be something like an inclusion operator, for instance. The interpolation space is this space here, B1, B2 in this bracket with the theta. That is the interpolation space. So what does this... So, yes, so this is the interpolation... Well, yeah, you can name it in the definition. So the point is that this is B1, this is B2. And then we have a theta here. And then the space that corresponds to this theta is exactly this space in the middle, right? So this is why it's called interpolation, because this corresponds to 0, this corresponds to 1. And then we're looking at functions that are fixed on these endpoints that map to B1 and to B2. And then when we move from one endpoint to the other, in the middle here at theta, we actually map out some Banach spaces. Right? That's why it's called an interpolation space, because it's coming from interpolating in the strip to an object that sits in a Banach space scale. Yes. Sorry, so you can call it an interpolation space. Well, it's not... Yeah, they are called interpolation spaces. So okay, so let's take some Hilbert couples, and let me and let S be non-negative self-adjoint operator on H3. So H3 is the space that this interpolation couple maps into, okay? With domain of S being equal to H1 and the domain of S squared being equal to H2. Okay? Then we find that H1, H2 interpolated is exactly equal to the domain of this operator S to the power of theta. So this is an extremely important theorem. And we will actually need a generalization of this later on. But that's why I didn't get too much into the construction of the Borel functional calculus or whatever, because these fractional powers, we can give meaning to it later. And this will actually be true for a more wider class of operators, and we will need that. But right now, this is all we need. Okay? So, S to the power of 2 theta. Yes, sorry, that's true. S to the power of 2 theta. Yes. Thank you. So what is the corollary now? The corollary is, so let lambda 1, lambda 2 be 2 Laplacians on E, right, over M prime. Then we have that H alpha Laplace 1 M prime E is equal to H alpha Laplace 2 M prime E. Okay? So what's the proof? You fix an alpha and then you let 2m plus 2 be larger than alpha larger than 2m. Okay, so then there exists a theta. So okay, so we fix that. Then there exists a theta. Okay, so before I say that, let me just point out the following. So from elliptic regularity, we already know that H2m plus 2 theta, lambda I of M prime E is equal to dom Laplace I 2m plus 2, and H2m M prime E is equal to dom Laplace I 2m. So, and by elliptic regularity, what do we have? We have that the domain of Laplace 1 to the k is equal to domain of Laplace 2 to the k. Okay, so we can fix the endpoints. Yes? Yes. We can, so by 2 Laplacians here, I mean with respect to 2 different connections. Okay. So anyway, by elliptic regularity, we have this at these endpoints, right? We've already asserted that fact. So, so then, therefore, for theta between 0 and 1, say, we have that H2m Laplace 1 M prime E H 2m plus 2 Laplace 1 M prime E. We know that these spaces are interpolation couples. That's what I showed in the last example. This is now going to be equal to H2m with respect to the second Laplacian, 2m plus 2 Laplace m prime e theta. And of course, this is now, you know, by what I wrote before, this is exactly going to be equal to h2m plus 2 theta Laplace 1 m prime e. And this is equal to h2m plus 2 because the operators Laplace I and all of their powers are self-adjoint, right? So we have this. So in particular, since we chose the alpha to be sitting between these two numbers, we have h alpha Laplace 1 me is equal to h alpha Laplace 2 m prime e. Okay, so therefore we can write or define h alpha m prime e equal to h alpha Laplace m prime e, i.e. we can drop the Laplace in the definition. Okay? So, I also talked about localizability. So, you know, what could we have done? Could we have gone through a local approach to building these spaces, right? So the problem is that, as I said before, that these Laplace alphas in Rn, so when we're looking at the Rn picture, these are not local operators. So Laplace alpha on Rn, not local for alpha outside of the natural numbers. So what can we do? So actually, interpolation theory is also really can be used to try and do a localization. It's quite remarkable this actually works. So let's define some things. So a map R between two Banach spaces, so we're back into the abstract picture again, is a retraction if there exists an operator S now from B2 to B1 such that RS is equal to the identity on B2. Okay, and then we call S a co-retraction. Okay, so very, very important theorem that I only learned a few years ago. I mean, I'm not an expert at all of this interpolation stuff, you know, so I only learned this a couple of years ago, or maybe 3 or 4 years ago. And you can find it in the book by Treble. I think it's due to him, actually, but don't quote me on that. It could be a theorem that's much older. So if we take two interpolation couples, as before, interpolation couples, and we have S in, say, B of bounded operators of B1 plus B2 tilde to B1 plus B2, which is a co-retraction to a retraction R in, say, b1 plus b2 into b1 tilde plus b2 tilde. Okay. Which restricts to bounded co-retraction and retraction from bi tilde to b and bi and bi to bi tilde respectively, then right, okay, maybe I should just stop here. Then what do we have? We have that s theta, which is equal to s now restricted to b1 b2 tilde theta into b1 b2 theta. So we know that this is bounded from before, has closed range and p theta, which I'll write as s theta r theta, is a projection such that s theta of b1 tilde b2 tilde theta is equal to p theta of b1 b2 theta. Okay, so what's this saying? It's saying that the space, so it's saying that inside this interpolated Banach space b1 b2, the range of s theta, which is a closed subspace, is complemented. Okay, so we can split up the space. So why am I telling you this? Okay, so why am I telling you this? So that's the theorem. It's a bit of a technical theorem, but bear with me for a second. So now let's return to the question of localizability, right? So proposition, well, I won't write it up as a proposition. I'll just write it up as a calculation. Maybe in the notes I'll include it in a cleaner form. So let's take covering of M prime by trivializing charts. Maybe I should include the trivialization here too. So because M is compact, we get finitely many of them. We have trivializing charts, and then let eta I be a partition of unity. So I equals 1 to k again. This is a finite partition of unity, or smooth partition of unity, subordinate to this, to the cover. Okay. So now let me do the following. So let me define the map S. So this is, I'm going to define a co-retraction from the Sobolev space M prime E into the Sobolev space 2M. So this is where we have local operators, right? Cn. But now I'm going to take the product of them. So I'm going to take k copies of H2n. And what is my co-retraction? So this of U is going to be precisely equal to phi composed with, okay, so phi 1 composed with eta 1 times u. So now this is supported inside the ui, psi 1, sorry. Oops. Dot, dot, dot. And on the last entry, I just have 1 replaced by k. Okay. Oops. So now, let me write the retraction. So now I have elements from k copies of H2M. And now what I'm going to do is I'm going to simply take the sum I equals 1 to k of psi I inverse composed with, okay, so let me see now. Psi I inverse, vi, and then I'm going to multiply by eta I. Yes, so this is really restricted to u. Okay, so this is really, I should really restrict this to ui. So maybe I'll write that. So this is vi restricted to psi I ui. And then I'm going to now composed with psi I inverse. Okay, so I think it's pretty easy to see that if you compose R with S, this is going to give you the identity. If that's not the case, then modify R so it does. Okay. So now we invoke, so now we have interpolation scale here in Euclidean space. So we've just taken a finite product of spaces. So again, we can check that these spaces interpolate. We have already shown that the H2M's interpolate and they can be equated with fractional powers of Laplacians on these vector bundles. So all of the hypotheses of this theorem, this co-retraction theorem, is satisfied. So what does it tell us? It tells us that S theta of H2M theta of M prime E is now contained in H2M theta Rn C capital N to the power of K, and that R theta S theta, so we can reconstruct the Sobolev space that we're interested in. So we have that this, this is exactly the property that it's the identity, right? So it's saying that we can also look at, even though these are non-local objects, so it means that what happens far away outside of this localization really doesn't contribute much. That's really what this is saying, okay? So you really need to use a theorem if you want to try and localize. So this is, the only reason I'm saying this is because it's really important to be careful when you're dealing with fraction order spaces, because it could be that it makes you fall outside of the realm of what you can do typically with differential operators, right? One of the nice things about differential operators is that they're local operators, and that immediately allows us to localize everything to Euclidean space. But using something like the retraction co-retraction theorem, even for the non-local counterparts, we can still try and do a localization. So what this also allows us to do then is it allows us to import already existing results. So it's much easier to prove results in the upper half space. And we can pull all of those results across now onto manifolds, at least ones that are compact. Okay. So now that we have this fractional stuff, and it's precisely the way you would prove the kind of theorem that I'm going to tell you next, is exactly through this kind of a retraction co-retraction theorem, right? So now let's get back to trying to understand the trace space, right? So remember, our goal is to try and define the map gamma on all of DOM Dmax. So let mu be a measured manifold with the boundary compact. Okay, that's all I'm going to assume. So let E be a bundle over M, HE a metric. Then the map RU, which is, so it was maybe a bad notation to use R in the previous theorem, or maybe it's bad to use it here, but anyway, we'll do it. So U restricted to the boundary. So this is a map on compactly supported functions ME to compactly supported smooth functions on the boundary. So this map is a bounded map from HK lock. So we already talked about the lock spaces. ME to HK minus a half. So this is why I needed to talk about fractional derivatives to begin with. Okay, so the point is that, okay, so let me finish the statement here. Oops. So this is, oh, okay, that's not so nice. All right, sorry. So, and this is for K greater than, so this is K in, so integer K greater than or equal to 1. Okay, so the reason I really wanted to mention the retraction co-retraction theorem is that you could prove this from pre-existing Euclidean results by knowing that you have a compact, a manifold with compact boundary, exactly by pulling everything down. I mean, you have these charts now in Rn+, and then you have a theorem of this sort in Euclidean space, and then you can just pull it across using the retraction co-retraction theorem. Okay? All right, but I won't get into the proof of that because, you know, I mean, I think it's clear how to get it from the Euclidean results. Of course, proving the Euclidean results is a different kettle of fish altogether. Okay, so now I wanna make another note or a remark maybe. So if M is compact, right? So it's compact with boundary. So we can assert, so remember in the compact case, we have the H alpha spaces and the H alpha 0, or the H 0 spaces, and we can construct also the H alpha 0 spaces, right? Of course, the H alpha 0 spaces are not of any consequence to us because they are exactly going to be the spaces which have for maps that are going to be 0 on the boundary. So it's going to be the kernel of this map R. So, I mean, by considering integer k and through interpolation, because this is for all k, we can assert that R from H alpha of ME to H alpha negative a half partial ME is bounded, one second, for alpha greater than a half. Yes, question. Yeah. So the question was, how is the boundedness on HK to be understood? So let me just erase that. Extends It extends to a bounded map. So that's why I set it on these spaces first, right? Because these spaces are somehow the essential spaces, and then we can extend it to a bounded map of this sort. Yeah. Yes. No, there's no connection between R being a retract and the boundary being a retract. You mean in the Treeble's theorem on this co-retraction retraction? I mean the R here, so the R in this case is not a retraction, right? This is just I'm defining R of U to be just U restricted to the boundary. So that's why I said that maybe that was a bad choice of notation, but well, I only noticed that now and I can't think of something else on the fly. The R in the previous theorem of it being a retraction means that, when we map from S to, into the range of S and then we compose with R, we get back the identity. That's where the retraction co-retraction language comes in, and that's not connected with the R in this theorem. I have no idea. I've never thought about that. So the question is this map a retraction if the boundary of the manifold is a retraction? I have no idea. Yeah, I've never thought about that. Sorry. Yeah. Okay, so this remark, so we can assert that this is bounded for alpha greater than a half. But the point is that we cannot get the boundedness of this into L2. Okay? So what that means is that the norm blows up as alpha approaches a half in general on Sobolev scales. So this is somehow a subtlety with boundary value problems. You need some extra information, something like solvability if you want to get to alpha equals to half and beneath that. Okay, so for these general Sobolev spaces, we cannot get to alpha equals to a half. So to go from alpha, but it's impressionistic, right? So if this trend was to continue, and suppose you can get from H a half to L2, then you can ask, well, what happens if alpha is less than a half? Because ideally you might want to know that you can get something bounded from L2 into some space here, but then we would be in the negative order spaces, right? So we need a notion of negative order. Okay, so to go from alpha equals to a half and below, so this is a bit more non-trivial, and in particular need negative order Sobolev spaces. Okay, so whatever that means. Yes. Well, the question is, what do you mean by local space? I mean, you can make sense of that now because we have this retraction co-retraction theorem, but you have to still be careful with what you mean by local real spaces. Well, you can say that, but the problem is that you still need to use something like the retraction co-retraction theorem to prove that that's a sound definition. Because the thing is that things get spread out to infinity, right? If you're non-compact. If you're compact, of course, this is not a problem. So there's this, of course it's not really a problem, right? You can do it. I just haven't stated it because I don't want to get into a technical kerfuffle, but that's something that you can think about. I mean, I think all the ingredients are there. You can just try and look at the retraction, co-retraction theorem because, I mean, when you're talking about these HK spaces, you multiply by something which is compactly supported, and then you're taking a norm. So you just have to make sure that all of these things are reasonable, that this is sort of well defined. But you're right, it can be done. Yeah. Okay. So so we have 10 minutes left. Okay, so let me see. Oops, yeah. Let me see. So what happened here? We went up to the top. Okay, so let me just maybe make a start on this. We can make some progress maybe. So, so let me now talk about negative order Sobolev spaces. Okay, so we restrict our attention here firstly to M prime compact and without boundary. Okay. So also just recall from before that L2 M prime E is equal to L2 lock M prime E. So this is again independent of both the metric and the measure, right? But of course this is as sets. I mean, when you want to compute something, you need to know So if you want to compute something, then you need to know that, you need to fix a norm and so on and so forth. But as sets, they're independent. Okay, so actually it's also convenient sometimes to think about L2 in this setting as H0. Okay? So now also recall distributions, right? So what are distributions? So of course we don't need the compactness for this, but this is going to be the topological dual space. So it's going to be the dual space, sorry, not the topological dual space of compactly supported smooth functions on the interior, and we topologize this with the inductive limit topology. Okay, because we can do that, right? In this setting, if you recall the calculations from before, we have that on a compact manifold when we look at taking two different sets of connections, raising them to the power of m, we look at their difference, they're going to be order m-1 differential operators. So that means that we can just construct distributions on these manifolds, and in fact we don't need compactness for this. Okay. So so why do we want this? Well, we always want to see these spaces, say L2ME, M prime E. Of course, I see this as a subset of the distributions, right? So how do I see this as a subset? Well, i.e. I take a F in L2, and then I think about F acting on some V. So I take a V in there, and this is just going to be the integral, the L2 integral once I fix a metric, right? It doesn't matter what the metric is. But I really want to see it as I mean, I know it's an identification, but from here on, we will always see L2 as a subspace, or yeah, a subspace of distributions. Because I want some breathing room, right? The thing is, I want to now look at going to a space larger than L2, so I want some breathing space. Okay. So now let me define. There is a prime missing, thank you. So let me now define a space M prime E. So this is a negative order Sobolev space. So I say it's in the negative order Sobolev space if the following norm that I'm going to define is finite. So I'm taking the supremum of the V in H alpha naught. So H alpha naught here, I mean, we're on a manifold without boundary. So this is just equal to H alpha. But I'm just writing it in this impressionistic form because if you want, you could do this also on a manifold with boundary, right? And then it's important the choice of space that you choose. So here you really should be in a space where compactly supported smooth functions are dense. Okay, but of course we haven't, I mean, these are also constructed by just taking an interpolation of these spaces at these integer intervals. Okay, so you have to construct it, but once you do, you're done. So I want this to be finite, right? So yes. This is V in the denominator. Thank you for that. Well, I cannot make sense of L2 here. I'm looking at just distributions, right? I'm looking at, oh, sorry. There isn't a prime here. So this is okay. So I'm writing a function f acting on V. So V here is in compactly supported smooth. Okay, sorry, yes. Here, I cannot talk about an L2 pairing, right? Because I'm looking at just distributions acting on V. So here I'm just talking about the action of the distributions. But you hit on a very, very good point, right? So the question is, how do we really understand, you know, exactly what's going on here when we restrict to L2? And that's really, so you've hit upon a point there, and I think in the interest of time, I won't get into it, but from next time, what we'll do is we'll really understand this norm when we take a U in L2, because, I mean, I'm considering L2 to be contained in this space here. So I can try and think about what happens now when U is an actual L2 section. And when U is an L2 section, of course, you're right, this is just going to be given with respect to the pairing. And then we can really aspire to try and understand exactly what's going on here. And in particular, we can understand the H minus alpha norm from an operator theory point of view. Okay, so that's what we'll do next time. And then I can finally tell you how to define the map gamma, which is the trace of U and all of its derivatives in the t direction, in the transversal direction, up to order m-1 on the whole domain Don D max. Okay, so that's what we'll do next time. Thank you. So, any more questions? I know that this is, the lecture today sort of encompasses a lot of technicalities, but I really think that if you're interested in working on these things, these are really the salient things that you should try and get a grasp on, because this really is a very powerful toolbox with which you can think about lots of things. So the question is, is there something you can do with this that you cannot do with the Fourier transform? Well, first of all, I mean, I know I've kept things to the compact setting, but the Fourier transform doesn't bode well when you go into the non-compact setting. I mean, if you want to think about all of these things, you need to have geometric assumptions in order to pull everything down. Sure, you can do that, but I mean, the thick and thin of it is, and this is why, even though I've done this in the compact setting, impressionistically, I've left everything at the level of operator theory, because the point is that you can still think about doing all of these things, thinking about fractional spaces, and so on and so forth, because the operators see infinity, right? Here, I mean, these operators are, I mean, this is a global definition. It's not a local definition. And the point is that you can look at it locally when you have nice enough bounds and so on and so forth. And then the way that you equate the things that happen at a local level with what happens at a global level is using things like the retraction co-retraction theorem. I mean, the theorem here, if you want to try and localize and you want to look at what happens, you know, on a non-compact manifold through localization, from an analytic point of view, what you really need is to be able to construct these retractions and co-retractions. That's exactly where things like bounded geometry assumptions would creep in, right? So it gives you a top-down view of what goes on. And if you want to use the Fourier transform, I mean, sure, at the heart of it all, in many of these theorems, especially in proving, I mean, even in a theorem like this where you prove it on a manifold, I mean, you prove this initially on the upper half space, and then the idea is that you import this to the manifold setting. And the way that you import it to the manifold setting is precisely by doing this sort of a retraction co-retraction trick. But the proof of all of this sorts of stuff in Euclidean space is through Fourier transforms and typically through Fourier theory. So yes, you could do a lot of this stuff using the Fourier transform and localizing, but then somehow you start to lose the global nature or the global picture. So I'd rather go from the global picture down to showing, you know, how they agree when you pull everything down to localizations. Does that answer the question? So if there's nothing else, let's meet on Wednesday and continue. Thank you. Will do.